Today's topic, the Nested Interval Theorem. This is another expression of the important basic fact that the real line is topologically complete. Some of the slides in this lecture are more dense than slides in other videos in this series, so I'm trying to keep it a little shorter. We consider an infinite sequence of closed intervals in the real line, each containing the next, hence a nested sequence. The more general terminology for a sequence with containment like this is a chain. The theorem says that for every such nested sequence of non-empty closed intervals, there's at least one point inside all the intervals. In other words, the intersection of all of the intervals is non-empty. And by the way, it's important here that our intervals are closed. Here is an example of a chain of non-empty open intervals for which the intersection is empty. In other words, there's no point inside all the intervals. Also, by the way, this theorem will not work over the rationals. And later in this video, you'll see an example where it does fail over the rationals. What do the real numbers have that the rationals don't? They're both ordered fields, but the real line is complete, which the rational numbers are not, meaning that, for example, the real numbers satisfy the least upper bound property. That's one expression of the completeness property. And that's the property that I'll use to prove this theorem, the least upper bound property. So far, these are the only two defining properties of the real numbers that I've mentioned. They're an ordered field with the least upper bound property. So that's what you have to work with. Here's our proof. The left endpoints of our intervals form a sequence which is bounded above. In fact, each of the b's is an upper bound. So, by the least upper bound property, the supremum of that sequence exists. Call it C. Since C is an upper bound, each AI is less than or equal to C. So, we only need to show that C is also less than or equal to each bj. And that's not hard. We'll prove this by contradiction. So suppose not, then there's some bj less than C. Wait a minute. C is the least upper bound for the a's. So if bj is less than C, it can't be an upper bound for the a's. That means bj is actually less than some ai. Now to get a contradiction, just take k to be the maximum of I and j. Then ak is less than or equal to bk, which is less than or equal to bj, which we're assuming is less than ai, which is less than or equal to ak. And that's our contradiction. Look, ak would be less than ak, contradiction. So that must mean that the theorem holds. As a first application of the nested interval theorem, we're going to prove the existence of square root of 2 in the real numbers system. But first, I want to remind you that the square root of 2 does not exist already in the rational numbers. This has been known for a long time, certainly to the ancient Greeks. Actually, the ancient Greeks recognized the existence of line segments whose length was square root of 2. Or rather, in this right-angled triangle, we have two sides whose ratio is square root of 2. However, for the ancient Greeks, there was a difference between geometric lengths of line segments and numbers. To us nowadays, this sounds like an overly subtle distinction, but to them, apparently, it was an important distinction. There was a line not to be crossed. Ironically, the whole point of contention is strikingly similar to many of the hang-ups that some people have today in accepting certain mathematical notions. Back to the proof, which is by contradiction. Suppose C is a rational number whose square is 2. There should be two square roots, one positive and the other negative, so we'll just take the positive square root. Now that would be a positive rational number, and therefore a ratio of two natural numbers, a over b. We can assume this fraction has been reduced two lowest terms. In other words, the numerator and denominator have no common factor bigger than 1. This is really the most subtle point of the whole argument because it requires well ordering, and I'll talk about that in a later video. But I'm pushing that under the rug for now because we want to race on ahead to get to the analysis that we care about. Cross multiply and square both sides to get a squared equals 2b squared, which, by the way, is an even number. So that must mean that a is even, right? Of course, if a were an odd number, then squaring it, you get an odd number. So I guess a must be even. So a is therefore 2d for some natural number d. Substituting that in to the previous equation and simplifying, we get b squared equals 2d squared, which again is even. And again, that would have to mean that b is even, right? I mean, if b were odd, its square would be odd. Contrapositive, if b squared is even, then b must be even. So that's easy. So b is twice e for some number e. And now we already have a contradiction because a and b are both divisible by 2, whereas we did say that a and b had no common divisor bigger than 1. So in conclusion, there is no rational number whose square is 2. Now for our proof that there is a square root of 2 in the real number system. We'll prove this using the Nested Interval Theorem. This, by the way, is a warm-up to proving the Intermediate Value Theorem, one of the first theorems you hear about in calculus, and you don't get a proof of it there. That's our job here. Our statement is just a wee bit stronger. We show that assuming C is positive, the solution then is unique. So there's a unique positive square root of 2. But before we get into the details of the proof, let's talk about the general idea. The height of the graph of y equals x squared on the interval 1, 2 goes from below 2 to above 2. So we expect somewhere in between, there's a point C where it exactly crosses that height of 2. The midpoint of the interval is 3/2, and there the function value lies a little bit above 2. So we're going to split the interval 1, 2, and we take the left half because it's on the left half that we must cross the line at height 2. And the midpoint of that left-hand subinterval is at 5/4, and the function value there is, again, below 2. So this time we take the right half of our interval. Going from 5/4 to 3/2, that subinterval should contain a root. Now we take the midpoint again, which is 11/8. So you see what we're doing here. We're zooming in to smaller and smaller closed intervals. And if we continue in this way, repeatedly bisecting our interval, we get a sequence of closed intervals which zooms in on our desired root. This is called the bisection method for finding roots. It's kind of an algorithmic approach to doing intermediate value theorem. So for a continuous function, this method will converge to a root. The existence of a root is a consequence of the intermediate value theorem, which we'll prove soon. We're not that ambitious today. It's just a test case for the intermediate value theorem. So returning to our proof, let's write down a recursive description of our chain of subintervals obtained by the bisection method that we described just a moment ago. Each subinterval is half as long as the previous interval in the list. So the width of the nth subinterval here, it must be 1/2 to the n, at least if you start at n equals 0. So after n bisections, we have an interval an bn of length 1/2 to the n, where an squared is less than 2 is less than bn squared. This is precisely how the subintervals are chosen recursively. Splitting the previous subinterval at its midpoint and saving whichever half, we see x squared crossing the line. But now that I've stated the recursive formula precisely, I need to take back some of the space on my slides because I need to use it for the next part of the argument. By the nested interval theorem, there is a point C inside all of these subintervals, a real number C. Now for every number n, the interval an squared bn squared contains 2, but it also contains c squared. So we have 2 points, c squared and 2, inside the same closed interval an squared bn squared. So that tells us that they cannot be any further apart than the width of that interval. And the width bn squared minus an squared can be factored as a difference of squares. And now this, you can see, is less than or equal to 4 over 2 to the n. Notice here that the first factor, bn minus an, is exactly 1 over 2 to the n. And the second factor is at most 4, since both an and bn are at most 2. That gives us our bound. Now the left-hand side is a non-negative real number, which must be 0, because choosing n large enough, you see that the distance between c squared and 2 is as small as you want. You can make the right-hand side as small as you want, so that forces the left-hand side to be 0. So that forces c squared to equal 2, and that gives us a positive square root of 2. We also point out that the function f of x here, x squared, is increasing on our interval. In fact, it's increasing on 0 infinity, and you don't need anything more than the axioms of an ordered field to see that, so the solution must be unique. Part of this proof makes use of mathematical induction, which will be the subject of the next video.